Oh, good evening, everyone. We're ready to go. It's a great pleasure again to welcome a speaker tonight that we've enjoyed before. And once again, this is Professor Lyall Hanton, and he's going to be talking tonight about the Haber reaction, the detonator of a population explosion. So welcome, Lyall.
Thank you. I've wanted to give this lecture for a while, so I'm hoping it's going to go well. So have I got a story to tell you tonight? So just imagine this. It's November 1918. The First World War has just ended. And the man who's responsible for the deaths of 100,000 people and probably the maiming of another million is awarded the Nobel Prize in Chemistry. What a controversy. Why was it that Haber was able to receive the Nobel Prize? In fact, it was so controversial that they presented the prize to him separately in 1920. In 1920, he had a separate ceremony. That there was no Norwegian royalty at the award of the medal, and he received the medal and made his speech. But he received. So why did he receive the Nobel Prize in chemistry, given that he was responsible for the deaths of so many people? That's what we're going to explore tonight. What he did was he solved the nitrogen problem. And so, what is the nitrogen problem? The famous British chemist Sir William Crookes said in 1898, sorry, that England and all civilized nations stand in deadly peril of not having enough to eat. And this was because, of course, of the dwindling supplies of natural sources of fixed nitrogen, which are needed for agriculture. And he was predicting that if something wasn't done, that there would be mass starvation by the 1930s. This was the problem that we're trying to sort out. And why was nitrate so important? And where did it come from? So nitrate farming practices, of course, allowed the growth of, allowed food to be grown, but of course they were basically at that stage almost medieval. Fallow fields, the use of things like legumes and other nitrogen-fixing plants to provide nutrients for the soil. But of course, that no one was prepared for sort of mass agriculture. And of course, nitrate has another use as well. Nitrate's not only used, of course, as a fertilizer, but it's used, of course, as I've got up there, saltpeter, a vital component of gunpowder. So if you want to wage war, then you have to have potassium nitrate or sodium nitrate, ideally potassium nitrate. And so for a long time, people have known this. So this is a nitery. And what happens here is King Charles I insisted that all his subjects provided the crown with bodily waste. So you would collect it up and it was provided and taken away because the nitrate in that bodily waste was so important. And it was spread out in these were sort of stacks of hay kind of thing. So you spread out the bodily waste over these hay stacks, and then you just slowly let it evaporate, and then you harvested the nitrate crystals as they came through. It must have been an awfully smelly and horrible process. And they processed it in this way. Why? Because gunpowder was so important. You couldn't wage war without saltpeter. And so this was how nitrate, particularly potassium nitrate, was made available. But of course, people started to find other sources of nitrate. One of the reasons that, in fact, the British colonized India was there were large nitrate deposits in India, and the British used those to make their weapons of war. And then when they ran out, there were large nitrate deposits discovered in Chile. So this is the Atacama Desert. You can see these sort of white, I presume these white crystals here are sort of probably nitrate deposits. Enormous deposit of nitrate. And you can see it becomes a total, in fact, the Chilean economy is built around the supply of nitrate to the world to be used for fertilizer and to be used for military purposes as well. And you can see here all these stacked up trains with bags and bags and bags of nitrate in this Chilean town, getting ready to supply it to the world. Nitrato of Chile. Here they are. You see, loading those bags into little boats to take out to these waiting ships that they're going to take it to Britain and to America and places like that. Here's a real photograph of these ships in the bay here in these ports. And by 1911, something like 2 million tons, sorry, not tons, 2 million tons of potassium nitrate was being exported from these ports. And you can imagine the fact that the Chilean economy, in fact, there are case studies done on the Chilean economy. It's a one-hit wonder, and as a result of that, Chile becomes a very wealthy country because it has these enormous supplies of nitrate. And I think if you go to Chile, you can see the wonderful buildings that were built rather like Dunedin in the gold rush, the beautiful buildings we have here built during the gold rush that haven't ever quite been replaced. I imagine it's similar in Chile. You'll find I imagine some beautiful municipal buildings as a result of the nitrate trade. But if you're going to wage war, and of course the First World War is coming, if you're going to wage war, then you want to prevent your enemies from being able to have the material that they need to wage war. And so the British blockade, because they ruled the sea at this time, the British blockade the supplies of nitrate for Germany. And so it was predicted that Germany had about 6 months worth of supply of nitrate. So the general feeling in Britain was that Germany would be able to wage war for about 6 months before they ran out of the vital ingredient, potassium nitrate. And so that was the thinking at the time. The British still were able to import nitrate because they controlled the sea. And so they were able to make their own explosives. And of course, those explosives just weren't gunpowder now. Nobel had come along with his, with his amazing explosives. So this is, nitrate, and you can see the nitro groups here. This is nitroglycerin. This is trinitrotoluene, TNT. You can see all of them have got nitro groups on them. So that nitrate is important in making those much more higher impact explosives that Nobel had developed at that time. Particularly dynamite, of course. And for all Nobel's wringing of his hands at the end of his life and the providing of the Nobel Prizes and the Peace Prize, he knew exactly what he was doing. He was making money, and he was making money by making chemicals that were explosive and damaging. Yes, they were able to blow cliffs apart and build a railway system in America as a result of these powerful explosives, but he also knew they were always going to be used for war. In fact, if you read his biography, about 200 people die at his hands, including his brother, as he tries to stabilize these very volatile and explosive materials as dynamite. So this is why people want nitrate, to make these high energy explosives so they can wage war. What's the problem with nitrogen? Why is it so? There's so much nitrogen. It's not like we're short of nitrogen. 70% of the atmosphere is dinitrogen. What's the problem? If it's there and available, why can't we use it in nitrate? Why these difficulties? Well, of course, nitrogen has a triple bond. So you can see there the 3 bonds. It's not just bonded singly, it's a triple bond. It's a very strong bond. And if you want to break that bond, it's not easy to do. And of course, that's why those materials are so explosive, because when you cause them to degrade, they immediately form nitrogen, giving off a large amount of energy. So it costs a large amount of energy to break those bonds. And of course, when those bonds are formed, a large amount of energy is given off. That's why those things are so explosive. So nitrogen with its triple bond, very, very difficult to break apart and use. Now, of course, nature, as always, clever nature has found ways of doing this. So plants like legumes and clover, here are the nodules in clover that fix nitrogen in a sort of symbiotic relationship with bacteria. These nodules are able to fix nitrogen from the atmosphere. And we've known this as humans for a long time. We've used that practice in our agriculture, clover to enrich the land so we can grow other crops on in time. So nature's been able to do this for a long time, but there aren't that many plants that fix nitrogen. And it's not so easy to do. So what did this man, Haber, do? He came along, and here's the Haber reaction. It's a very simple reaction. He takes nitrogen and hydrogen and reacts it to give ammonia. Now, this is a very simple stoichiometric reaction as a chemist, and we use it to teach stoichiometry, because the other classic reaction is hydrogen plus oxygen to give water. So 2 molecules of hydrogen plus 1 molecule of oxygen gives 2 molecules of water. But that's a 2-to-1 ratio. And that's well, actually, it's not that easy for my students these days mathematically, but it should be easy for them. But of course, when you've got the Haber reaction, you've got 3s and 2s. And this makes it just a little bit more tricky for them to work out the stoichiometry. So it's a really good reaction to set problems around for first-year students. So it's a classic piece of equilibrium. And of course, what you've got to do is you've got to break this triple bond. And my pointer comes, oops, sorry. You've got to break this triple bond. I've lost my pointer. There we go. You've got to break this triple bond, react it with hydrogen to get ammonia. Then once you get ammonia through the Oswald process, you can end up making nitrate. The first step is to get ammonia. And the problem is, how do you do this? It's not easy to break that bond. And what did Haber do? He just used brute force, basically. He was going to take those molecules and he was just going to bash them together essentially. Because you can see on this side of the equation, there are 4 molecules. There's 1 molecule of nitrogen and 3 molecules of hydrogen. So there's 4 molecules on this side, and on this side of the equation, there's only 2 molecules. So if you compress things really, really strongly under an enormous amount of pressure, of course, the gas molecules are going to want to form the least amount of space. And that means they're going to make the smallest number of molecules. So in other words, which way are we going to push that equilibrium? That equilibrium, if we squeeze this stuff, if we squeeze these components together, these 4 molecules here are going to be taking up much more space than these 2 molecules over here. So if you put them under enormous pressure, you're going to force this equilibrium to go to the right and make more ammonia. And that's how you're going to make ammonia, putting it under enormous pressure with the right catalyst. You've got to have the right catalyst. And Haber, as a member of staff, I think he was at Karlsruhe University at this stage. He was also, he obviously wasn't earning enough money, so he was moonlighting, working for the Osram Light Company. And the Osram Light Company were trying to develop, the electric light bulb was a new thing, and they were trying to work out what was the best metal to use as the filament in light bulbs. And things like tungsten were used. And of course, the reason that the light bulb company, you've probably heard of Osram as a light bulb company, the reason it's called Osram was because they were making filaments of osmium metal, very expensive metal. In fact, they had virtually the world supply of osmium metal. It's a rare and expensive metal, but they had the world supply of it. So Haber just borrowed a little bit of the osmium to use as a catalyst, and he found it was very effective because he'd been working his way through various metals, and he used that as a catalyst to effectively make ammonia. He also found that later on that uranium was better, still an expensive metal to use, but not nearly as rare as osmium. And so he manages to push these molecules together. And here's his apparatus. This is it. This is the apparatus he used because he's doing it on a lab scale. So you can see enormous pressures. He has to develop, this is the thing, we forget, he has to develop, these reactions are being done under about 200 atmospheres, which at the time was very difficult to achieve. And so he had to develop seals, and he had to develop the equipment, to be able to stand that pressure. He had to be able to leak the gas in at the right rate so the reaction would take place. He had to be able to control all of those factors. Hydrogen is a tricky little molecule. It'll sneak out of any little gaps that are there. It also embrittles metal as well. So it's not easy gas to work with. And he has to overcome all of these problems. And this is the piece of apparatus that he uses. And I think in I can't remember the date now, but in sometime around sort of 1911, 1912, he makes about a milliliter of ammonia, and he's ecstatic because he realizes he's cracked the problem, and he can do this. And if you look at this apparatus, you'll see down here, as I said, you have to develop technology. You can see these beautiful, they just look like ordinary taps, but they're not ordinary taps because they're taps developed by this man. So this is Robert Rosengold. He's an English chemist, and he was interesting because not only was he a chemist, but he was also an engineer. He had an interest in engineering. So he was able to solve some of those chemical problems. He was working with Haber. He'd gone to his lab in 1906 and had been working with him, developing this process. And he developed, Rosengold developed this particular needle valve. So this is a needle valve, so that you could carefully control the small amounts of nitrogen or hydrogen that you needed for the reaction. And you can see those Rosengold needle valves here in the taps in this particular apparatus. This apparatus sometimes is referred to as the Haber-Rosengold apparatus. And one of the things that Rosengold subsequently, he worked for Haber right up until the beginning of the First World War. He was interred in Germany during the First World War, but allowed to continue working because making ammonia was very important. Then after the First World War, he returned to Britain where he worked for the General Electric Light Company. They all seem to be working for light companies. And he always said of Haber that Haber was a very honest man and that Haber continued to send the money from the patents because he was named in the patent for the production of ammonia. So he was receiving enormous amounts of money from, of course, Germany underwent hyperinflation after the end of the First World War. So he didn't get, some of that money fell away, but he said later in life that he had enough money, and he was a serious philanthropist. So he received a lot of money from those patents as a result of the work that he did with Haber. And Haber couldn't have done that without that sort of engineering. Haber described his reaction as bread from air, taking nitrogen from the air, turning it into fertilizer, and so you could grow crops and therefore make bread. That was his kind of classic line. And this is the Nobel. This is the Nobel Award, and you can see it was awarded in June, unusual time, June 1920, because of that special ceremony that had to be held for Haber because of the general resentment, and people felt that it was inappropriate. Before we come to why and what Haber did, there's another player in all of this, and this is Carl Bosch. In fact, quite often, you probably know, quite often the Haber reaction is referred to as the Haber-Bosch reaction, because Bosch is really an important player as well. Bosch is a chemical engineer. In fact, his family, the Bosch family, is the family you perhaps know of. They're the people that make Bosch ovens and Bosch fridges and Bosch washing machines. I think it was his uncle who set that company up. So he's related to those people. So the companies that he's involved with still exist today. But Bosch was a chemical engineer. And I don't think Bosch and Haber got on particularly well. Haber got on particularly well. Bosch says of Haber, he does not concern himself with the big picture, only with the glory of invention. He's not worried about trying to make it work. Because, you know, at the moment, what we've got is we've got the small piece of equipment on a lab bench making, you know, a few millimeters of ammonia. That's not going to solve the problem. So Bosch's task was making this work on an industrial scale, and that's what he does. That's what he's good at. And imagine what he's got to do. You know, he's got to make seals. He's got to develop pressure apparatus, not the small pressure apparatus that Haber's got. He's got to make pressure apparatus which is 2, 3, 4 stories high to put this under pressure so they can make enormous amounts of ammonia. Remember, because Germany's about to go to war, and they need this nitrate not to feed their people, because in fact many of the German population starved during the First World War because they're not growing crops. They need the nitrate to make explosives. And so this is the plant that he sets up. BASF set up this plant at Oppau, and you can see this, you can get a sense of the scale of it. This must have been built, I mean, I'm amazed. This, you know, Haber's doing this, the Haber reaction, lab bench scale, 1911, 1912, and then by 1915, they've got this full-scale plant, you know, producing enormous amounts of ammonia. And, you know, and in New Zealand, we struggle to get a tunnel under Auckland or build a hospital in Dunedin. And yet, you know, here we've got, you know, this amazing plant built, you know, in 1911, we're a long time ago. They're still able to whack it up pretty quickly. And so this is the size of the plant here. So this is the BASF plant at Oppau. You can see the size of it. It's really large. And then because, of course, they're wanting to gear up their war efforts, they built another plant at Lyall in 1916, an even larger plant. Bosch becomes the president of BASF, which eventually becomes this company called IG Farben, which we'll feature in a moment. And you can see Bosch promises the German government that he will produce tons and tons of ammonia. So over the period, these plants produce 500,000 tons of ammonia for munitions almost every year until the war ends in 1918. So enormous amount of ammonia provided to make nitrate for the German war effort. And you know, this was of course a war that was fought without very much aerial bombardment. You know, today these plants would have been destroyed by drones or by mass bombing or something like that. But in the First World War, that was much less common. So these plants were able to function, you know, without being able to be attacked really very easily by the Allies. And in 1931, Bosch, the first chemical engineer ever to receive the Nobel Prize, the first engineer to receive the Nobel Prize, he receives the Nobel Prize in 1913. Why so long? Well, the impact of his work had to be fully appreciated. He was a chemical engineer. There's a little bit of resistance to offering him the Nobel Prize in chemistry. And also he was slightly tainted by the fact that he had become the director of this company, IG Farben, and IG Farben had been closely associated with the Nazi Party at this stage. He had been allowed to continue as a director by of course, we haven't really discussed this in any length. Haber himself was a Jew, so you know, this was creating all sorts of problems. He was a Jew who converted to Christianity in order to progress his career. He wasn't a practicing Jew, but he converted to Christianity so that he could be appointed at a German university and move forward in his career. Bosch wasn't a Jew, but he was director of this company that was associated with the Nazis, and so he was tainted slightly. People were just sort of people were concerned about that, and it's probably why it took a little while for the prize to be awarded to him. Haber, of course, Haber is an interesting man. When when I first heard about him, I thought that he was, he's often characterized as an evil genius. And I think that's probably too harsh. I mean, that's how I've often characterized him when talking to my students about any excuse to sort of drop the Haber reaction into a discussion. And that's how I would have portrayed him until I recently read a biography of Haber. And he's a much more complicated man than that. A very strong German patriot. And you can see that from his comments there. During peacetime, a scientist belongs to the world, but during wartime, he belongs to his country. So he's already making an enormous contribution to the German war effort. They're able to produce nitrate and so therefore make explosives and continue to fight. But that's not enough for him. He wants to do more. And so he begins to think about developing war gases. So he's the person who kind of name is associated with using war gases. And he starts to think about what sort of war gas could you use? And there've been various attempts at various stages in various wars to use chemical weapons, not very successfully. But he thinks about what he could use, and he decides that the best gas to use would be chlorine gas, because chlorine is heavier than air, and it would fill the trenches, and it would asphyxiate the soldiers in those trenches. And that's what he sets about doing. So he plans this. They use thousands of tons of chlorine. They set these cylinders up, and then they've got to wait for the right wind conditions, because of course you don't want the chlorine being blown back over your own troops. And you can see the sort of efforts here. I think they use it against the Canadians in one of the battles of Ypres. And so there are the gases there. Here's Haber himself in his military uniform. By now, he's a captain in the army, getting ready. These are shells. These are chemical shells loaded with probably chlorine or something like that they can shoot over, because the technology for chemical weapons was constantly evolving. And here's a cartoon or a drawing showing Haber, releasing the gas over the troops. And the first time they released it, of course, nobody was expecting it. So it's just a horrific weapon. And the general view is that it wasn't a very effective weapon of war. But its psychological effect was enormous once people realized what was going on. And the first time they use it, the German troops are not able to capitalize on the fact that the Allies have been knocked out and moved through the breach, because the German army was away fighting on the Eastern Front. And so they lost the opportunity. Haber was furious. He'd used this weapon. It had worked perfectly well, just as he expected. He'd had an enormous impact, but they couldn't capitalize on it because, eventually the gas blows away, and the German soldiers weren't able to move forward. And, this is the sort of aftermath. This is the famous painting by John Singer Sargent of British troops being led away after a gas attack. Here's the real thing. Here's the real thing here. And Haber wasn't just interested in chlorine. He developed mustard gases. He was an enthusiast for developing weapons of war. He said, and here's and of course the problem is, and this was what the Germans worried before they deployed chlorine. If we show our hand, then it won't be too long before the Allies are using the same weapons. And of course, that's exactly what happened. So here are German soldiers now wearing gas masks because the British are also using gas weapons now against the Germans. So those weapons became used extensively during the First World War. And people were horrified at the use of gas. But Haber said, death is death, no matter how it's inflicted. Is somebody dying from asphyxiation any worse than somebody having their, arms and legs blown off? That was kind of his view. He took the view rather like he felt that those people who thought that gas weapons were not a legitimate weapon of war would be rather like the French knights at the Battle of Crécy when the English archers shot them down. The bold, noble French knights were, laid to waste by the common English archers who took them out. And the French thought that wasn't really fair play, knight against knight, it should be. And Haber had this view. He felt that, gas weapons were a legitimate weapon of war. That was his view. Now, Haber, if we just return to a slightly earlier time, you can see Haber was quite a handsome-looking man when he wasn't bald, when he had hair, and he looks quite handsome. And at 27 years old, he marries this woman here called Clara Immerwahr. Now, Clara Immerwahr is a really interesting person. She's the first female student in Germany to receive a PhD. She worked with this man, Richard Abegg, and Richard Abegg was a friend of Haber's. And so Haber saw Clara, around the place, and he thought she looked very attractive. And so he wanted to date her, took her out, and eventually they married. And they had a child together, Herman. Now, Haber was not a very good husband. You know, he's director of the Kaiser Wilhelm Institute, as we'll see. He's busy with his war gases. He's got the Haber reaction to deal with. He's won the Nobel Prize. He doesn't have time for his family. And so when Clara marries him, of course, you know, she finds herself having to do the domestic chores that were expected of the time. She has to look after the son. She's got to keep his house tidy. She's got to prepare meals for him. And she goes crazy, basically. She's appalled at having to do this. She becomes depressed. She was a feminist, and also, significantly, she was a pacifist. And so when she finds that her husband is developing these war gases and doing this with great enthusiasm, she takes a service revolver one day and shoots herself in the heart. She doesn't quite kill herself, and unfortunately she's discovered by their 14-year-old son, but she dies the next day. So she just couldn't live with Haber. Now, various people have different views about this. It's unclear whether it was her just general depression about being constrained in a household and not being able to pursue her chemical research, or whether she was really appalled by her husband's desire to kill people. But nonetheless, she takes her life as a result of that. Haber, but Haber, unperturbed, the next day, he goes off to the Russian front to watch the release of the next chlorine attack. So he doesn't really spend much time mourning. So like I said, he's not much of a husband. Nonetheless, he marries again. So 2 years later, he marries Charlotte Nathan, and they have 2 children. Actually, they're twins, as it turns out. And that's about her story. That she eventually ends up in the UK with her children. So Haber becomes the director of the Kaiser Wilhelm Institute, where he's running a large group of 50 or so people funded, doing all sorts of research. This is post-war now. And one of the things is Haber's a man of great energy, and he's very creative, and he wants to do something worthwhile. And he thinks, well, Germany now is under the Treaty of Versailles. They've got these enormous war reparations to pay. How could he help Germany pay for these? How could he help Germany pay for the reparations that need to be made? And he thought maybe it'd be possible to get gold out of seawater. And so they did some analysis, and of course this is what we would call trace metal analysis now. They do some analysis, they get the numbers, and Haber thinks it's possible. And so for the next 5 years, he has these secret teams going around the world collecting samples of ocean to try and measure the amount of gold in the ocean, because it varies from place to place. And unfortunately, the original numbers that he got the first time he made those measurements that got him so excited about this, of course, they didn't know how to make measurements at that sort of level. So samples were contaminated, and the values that he got were too high. So when he finally, and he does a really good job, over 5 years, he essentially invents the area of, of analyzing trace metals at very, very low concentration. And he works out eventually that there's around about 4 nanograms of gold per liter of seawater. So in other words, you get a gram of gold in 100 million metric tons of seawater. And he figures out that it's just not worth it. And that figure is actually not too far off the current figure that people would claim was about right for gold. And of course, it's all very complicated, because gold is there as gold 1, probably gold 1 plus, with a bit of gold 3 plus. And you're going to have to electrolyze the gold in order to get it out and use it. And after 5 years research, he realizes it's just not going to work, and he has to abandon the idea. And he's quite destitute. He really wanted this to work. He thought it was possible. Another success after the Haber reaction, gold out of seawater, save the German economy, make the world right. That was his idea. And this is him. I imagine this is actually looks like a furnace of some sort. I couldn't find any pictures of because he was going to use electrolysis. I couldn't find any pictures of the electrolytic equipment he would have used to try and recover, or his experiments associated with recovering that gold from seawater. This was the best that I could do. Here he is with one of his assistants in his lab, and he was renowned for health and safety. He was renowned for smoking a cigar in the laboratory. He would storm in with a cigar and sort of hold court. He was he had a very loud voice, and he liked to smoke a cigar. So that was him as the director of the Kaiser Wilhelm Institutes. which have now become, they've evolved into what today we would call the Max Planck Institutes. So those kinds of Wilhelm Institutes have become the Max Planck Institutes. And so what's his legacy? The Haber reaction. You know, did he deserve the Nobel Prize in 1918? Well, I always find this amazing. You know, throughout human history, the population of the Earth from ancient Egypt right through until 1915-ish, the population of the Earth had managed to grow to 2 billion people. And then within about 100 years, it's suddenly 8 billion people. Why is that? Well, one of the reasons I would argue is it's the Haber reaction, because we can feed a population of that size. You know, it was pointed out we would not be able to feed that sort of population. Starvation in 1930 was predicted, but thanks to the Haber reaction, we can now feed a population of 8 billion very effectively. Actually, with too much waste, to be honest, but we can do it. Also, I'd have to, I guess, acknowledge Terence and this med school we're in. You know, undoubtedly modern medicine has had a role to play as well in the sort of quality of life, and we live longer. All of these things have been responsible for increasing the population. But I put it down mostly to the Haber reaction. This enormous increase in population, which occurred about the time, you know, the Haber reaction kicks off, and we have endless supply of nitrate for fertilizer and the like. You know, the Haber, and this is why I wanted to give this talk. You know, I call the Haber reaction the second most important reaction, and nobody's heard of it. You know, first important one, photosynthesis. Second most important one, the Haber reaction. It's conducted on a scale which is unimaginable. It uses 1 to 2% of all of the energy that we as humans generate in the world. 1 to 2% of that energy goes into the Haber reaction. It uses 3 to 5% of the natural gas in the world in the Haber reaction. And 50% of the nitrogen and amino acids in your body will have gone through an artificial Haber reaction. So roughly 50% of the population of the Earth today is here thanks to the Haber reaction. So 4 billion people probably have Haber to thank for their lives. So here's a man who killed 100,000, was responsible for killing 100,000, maimed another million, but has saved the lives of 4, 6, 8 billion people. How do the scales of justice, you know, how will he be weighed and measured when the time comes? Well, the time has come for him, he's dead. But you know, how will that go? Does saving 4 billion people make up for the 100,000 that was killed at his hands? I don't know. It's an interesting philosophical question. But you know, this is the fact about the Haber reaction. 50% of the nitrogen in our amino acids has gone through a Haber reaction. And you know, it's conducted on a large scale. Here's a modern Haber plant. You can see the size of it. You know, these are the big retorts, the big pressure vessels to make ammonia. Ammonia is being made on an alarmingly large scale for fertilizer, for all of the things that we need nitrate for. And of course, basically, Haber and Bosch opened Pandora's box, because now we have free nitrate for all. We no longer have to find piles of guano, or we no longer have to mine nitrate from Chile, you know, to grow food. We can do it artificially with the Haber-Bosch reaction. And of course, that means we waste it. 40%, I think the value, ChatGPT tells me, 40% of the nitrate that's spread on farms and soil and the like is basically washed into the ocean. So it's only about 60% effective. And we're probably putting too much nitrate on our soils. I heard recently Gore, for example, has nitrate in the significant levels of nitrate in their drinking water. So, you know, as humans, we've kind of wasted that gift that we discovered in 1915 with the Haber-Bosch reaction. But there's another dirty secret to the Haber reaction as well. And this is something nobody talks about. And that is, of course, if I go back to that reaction, one of the key components is nitrogen from the air, but the other key component is hydrogen. Where does the hydrogen come from? The hydrogen comes from natural gas. And that's why the Haber reaction uses 3 to 5% of the world's natural gas in making ammonia, because we've got to make that hydrogen first of all. So I think this is called the water gas reaction. You take methane, when it comes back to me, you take methane, you react it with water, and you make carbon dioxide and hydrogen. And for every 1 ton of hydrogen you make, you're going to make 9 to 12 tons of carbon dioxide. So a reaction which is being conducted using 1 to 2% of all the energy that we as humans create is generating a truckload of carbon dioxide. It's just unavoidable. Now, of course, it doesn't need to be that way, but my comment would be, have you ever heard any of these people ever talk about the Haber reaction in terms of climate change and the need to reduce, say, well, I've heard perhaps some of these people talk about reducing nitrate levels, but do they realize that by reducing nitrate levels, you would therefore use less, the Haber reaction would not be required so much, you would generate less CO2 as a result. They've never put that together. And I guess my point here is, if you're going to try and manage or try and understand and work with climate change, you've got to understand the drivers. And the Haber reaction, as I think I've got it up here, generates about 3% of carbon emissions in the world. So, you know, that's quite significant. And it's something that I've never ever heard discussed. You know, and this reaction, as I say, is conducted on an enormous and absolutely enormous scale. So there's a challenge, I think. And that's why I want to talk about the Haber reaction. But of course, we can generate clean hydrogen. You know, hydrogen comes in different colors. So that hydrogen I was talking about there, generated from methane, is called brown hydrogen because it's dirty coming from methane. Then there's blue hydrogen. Blue hydrogen comes from using electricity, which is generated by nuclear power. That's blue hydrogen. It's not quite green, it's blue because it comes from nuclear power, and that's not really so eco-friendly. Do something with all that nuclear waste at the end of it. So we've got blue hydrogen, and then there's green hydrogen made by, you know, by countries like our, potentially by countries like our own that, you know, have enormous resources of hydroelectricity. Countries like Norway and ourselves, we can make green hydrogen and use that in the Haber reaction. So the Haber reaction doesn't of itself generate CO2. It's the need for the hydrogen that generates CO2. And, you know, as we're trying to move, as there's talk of moving to a hydrogen economy, the challenge is, where does that hydrogen come from? Because a lot of the hydrogen that's generated in the world is dirty hydrogen made from natural gas. If you're going to move to a hydrogen economy, you've got to do it cleanly. And that's the challenge, I think, for any country that's going to use hydrogen in fuel cells to drive cars or whatever, power your house. It's going to have to be clean hydrogen. And there's a real challenge there because, of course, if you take water and you electrolyze it, that process is never 100% efficient. Even with the best catalysts in the world, it's not going to be efficient. And I should say, I've got to mention when I was talking about the Haber reaction, what Bosch did, not only did Bosch develop high pressure chemistry on an industrial scale, he also changed Haber's catalyst. He decided uranium was too expensive and osmium wasn't a goer. And instead he developed an iron catalyst. So the Haber reaction uses a cheap iron catalyst to generate ammonia. So Bosch had a really enormous effect on the production of ammonia. So, Port Haber, 1933, he's a Jew in Germany. And of course, this man is coming to power and he is forced out of his position as director of the Kaiser Wilhelm Institute. So, and many of his scientists had to go as well. Many of them decided to leave the country because it's just too dangerous now to be in Germany. So Haber goes to England, to friends in England, because he was friends with all sorts of people. Einstein, Otto Hahn, Lisa Meitner, Niels Bohr, you know, all of the great scientists of the day were within Haber's circle because he was such a creative and important scientist. So he goes to Cambridge for 3 months, and the story goes there that when he met Ernest Rutherford, our own Ernest Rutherford, Rutherford refuses to shake his hand because, you know, Haber was responsible for the deaths of so many people. So there's a story where Rutherford sort of ices him when he's there. So he wanders in the wilderness, sort of couch surfing for a while. And then he's offered it's suggested that he becomes the first director of the Weizmann Institute, which I suppose will be in Palestine at that stage. Israel doesn't exist as a state in 1934. So he's going to Palestine to become the first director of the Weizmann Institute. And on his way there, his health has been deteriorating for some time. On his way there, he dies of a heart attack in the Hotel Euler here in Basel at 65 years old. And so that was kind of the end of his legacy, really. However, there's, and so here's, if you want to read more about Haber, there's a wonderful autobiography, there's a wonderful biography by this man, Daniel Charles, which you can get on a Kindle at $14, as I found. The book itself is more or less unattainable, but you can get this on a Kindle, and it's a good read. And it was really it was Daniel Charles that kind of changed my mind about the sort of person that Haber was. He's not the evil genius. He's just a man who is a very strong, a great scientist and a very staunch patriot. So his godson, who's an historian, says, we must remember Haber in all his complexity. He was a man of science greatness and deeply cultivated, but excess of patriotism, he invented gas warfare, which has come to define the unspeakable horrors of the First World War. And then he was a very good friend of Albert Einstein's. And Einstein said of him, of course, they had very differing views. Einstein was a pacifist and certainly didn't approve of what Haber was doing and the approach that he took. And of course, Einstein left Germany very quickly and remained in America, where Haber tried to stay in Germany for as long as he could. And Einstein says of him, Einstein concludes that with regard to his tortured relationship with Germany, Haber's life was the tragedy of the German Jew, the tragedy of unrequited love. Haber loved Germany, but unfortunately that wasn't returned because they eventually get rid of him. And probably the greatest irony is that in the Kaiser Wilhelm Institute, they are trying to develop a new insecticide. Why you would use hydrogen cyanide as an insecticide, I'm not quite sure, but they invent this. They invent this new, or not new. They invent this this insecticide, or manage to sort of formulate it, called Zyklon, and it's used for killing moths and other insects in crops, so that crops can be grown. So it's used as an insecticide. It's hydrogen cyanide based, prussic acid, and of course, although Haber wasn't directly involved in the research, he was involved slightly in the research at his institute, but these two people were credited with the development of Zyklon. And in Zyklon, they had a particular smell, so that you knew that it was dangerous if you were exposed to it. But when the Nazis came to power, they took note of Zyklon, and Zyklon B was developed, which essentially was the same thing as Zyklon, except they took the odorant out. And of course, this was used to kill the Jews in the concentration camps. And in fact, some of Haber's relatives died at the hand of the compound that he helped develop. So there's a great irony there for poor Haber, although he probably never knew that. Right. So that's Haber's legacy. And as I said, I don't know how you weigh him up. And he solved the nitrogen problem, but the bad news is we have a problem ourselves. So the nitrogen problem has been solved, but the P problem, the phosphorus problem, has not been solved. And if you want to do a bit of Googling, you can, and you'll find that there's debate about whether we've passed peak phosphorus. Because the unusual thing about phosphorus as a vital element to life, the unusual thing about phosphorus is it doesn't have a gaseous oxide. So things like nitrogen and sulfur, carbon, those are all recycled through the atmosphere, through various atmospheric processes, because they have a gaseous oxide. So they can be recycled and we can reuse them in that sort of way. Phosphorus doesn't have, its oxide is not gaseous. And Asimov says, life can multiply until all the phosphorus is gone. And then there is an inexplicable halt, which nothing can prevent. Why is this a problem for us? Well, what are we doing? Think about the phosphorus. So the phosphorus comes from us. We're the source of phosphorus. We weed out and all that. And what do we do with all that waste? Of course, modern plumbing, it all gets flushed down the toilet and ends up in some treatment plant where the worst parts are, the bacteria are killed off, and then it's just, where does it go? It goes to the ocean, where it gets diluted like the gold. So we are slowly washing away all the phosphorus. New Zealand, for example, gets its phosphorus for agriculture, slightly dodgily. I mean, I think we spread most of Nauru over New Zealand. Now we're getting our phosphorus from sub-Saharan, which is, I think, the UN has criticised us for bringing phosphorus from that particular region that's in dispute with other countries. But phosphorus is a vital element, and we are, just as humans, we are just simply washing it down the sink. Think of all those the detergents we use, those wonderful those phosphate detergents that we use that clean our clothes. Again, phosphorus just being wasted down the toilet, and so this remains a problem. As I said, if you look on the web, you'll find some people think we've passed peak phosphorus. In other words, we're rapidly running out of phosphorus. Some think we haven't quite approached it yet. But retaining phosphorus is really, really important. And at the moment, we are just washing it into the ocean. So there's the challenge. Nobody has yet solved the phosphorus problem. And as Asimov said, when you don't have phosphorus, there's going to be no life. It's all over. So there's a challenge for humankind in the future. And on that note, I will finish. Thank you very much.
Time for questions. Look, I've got a question. You said early on in your talk that Germany had 6 months of nitrogen available for explosives. So if this process were not developed, what would have
The war would have
6 months? The war would have finished.
That would have it, more or less. They didn't have ammunition. Other countries wouldn't supply them. The Axis powers, they would have run out of resource.
So there's an alternative, really.
And I think if you were Germany, you wouldn't have actually embarked on a war with only 6 months reserve. I think the Germans knew that they were going to be able to use the Haber process to provide, because they were going to need to fight. The Allies didn't know that at the beginning. And so I think that was the challenge, because they had stopped the export of, so the Allies were still using nitrate coming from Chile. And that nitrate from Chile continued to be used for agriculture for quite, well into the Second World War. And now I think most of it's made artificially. But that trade in Chilean nitrate, it was a horrible trade. That you had the native Chileans digging it out, and it was in this inhospitable desert. It wasn't a very nice process.
Yes.
But the war would have had to have ended. They wouldn't have actually been able to. I don't think they'd have ever embarked on war, only having 6 months reserves, roughly 6 months reserves of sort of nitrate to wage war.
Other questions?
Hey.
So when did the British and the people on the other side of World War I become aware of what was going on in Germany with the Haber reaction? Was it before the war? I mean, surely they must have known about it before the war.
Secret. But I just don't think that anybody, I think the technology required to build those plants like the one at Boppau just wasn't in the hands of the British. The story I tell about, Britain, there's a lesson here for New Zealand as well. Britain, so Mellor, some of you will know the Mellor laboratories, and the famous chemist Mellor. Britain had given up the ability to be able to even make iron. It was importing the necessary kiln material. Was coming from places like was coming from Germany. In fact, most of the kiln material was coming from Germany and Belgium for the smelting of iron. And of course, when war breaks out, Germany won't supply you with ceramic material you need, to smelt iron anymore to make guns. And so Mellor has to go ahead and try and develop similar sorts of clay materials so that they can continue to melt iron. And so I think it was the technology. The British knew about the plant, but didn't probably have the ability at that time to be able to make and build those plants, and probably didn't think it was necessary because they were getting what they needed from Chile.
Other questions? Yes.
When TNT explodes, it's a gas explosion. Is it nitrogen being released?
Nitrogen. It ends up being nitrogen. Yes,
it is.
I believe so. Yeah. So you reform those 3 bonds, gives off an enormous amount of energy, and you've got a large number of moles of gas being. So it's the energy plus the gas that provides a sort of percussive effect.
Okay. And the other thing, you say nitrogen, triple bond nitrogen is quite stable. Carbon, triple bond carbon is unstable. Acetylene. It's what a difference between
with the
two elements.
Different. Yes, I guess that's a good point. Really. Yes. I don't have an answer for that. It must just be the bond must be stronger between the nitrogens and the 2 carbons. Yeah. Good point.
You were talking about the formation of hydrogen from natural gas and releasing that large amount of carbon dioxide. But if that gas is burned to just provide heat, it still releases almost the same amount.
It will. Yes, it will. That's right. Yes.
So whether it's used for heating,
yeah, that's right,
or for producing hydrogen, it's the same amount of carbon dioxide.
Fair point. Yes.
Yeah.
But then yes, I guess that's right. Yeah, you're quite right.
Other questions? We got any online questions?
If you weren't going to use it in the Haber reaction, then you wouldn't have to burn the gas, I guess would be what I would say. But fair point.
No. I don't think we have any more questions coming online. I'd like everyone please to join me in thanking Lyall for a wonderful presentation.